You know, inside every single one of your cells right now, there are millions of tiny biological machines called enzymes. They're making life happen at a truly incredible speed. But here's the thing, not all enzymes are built the same. So how do we actually measure their performance? How do we put a number on their speed and efficiency? Well, that's exactly what we're going to crack into today.
I want you to think about it like this. If enzymes were cars, some of them would be absolute supercars, hitting top speed in seconds. And others, well, they'd be more like old clunkers. So we're basically going to be detectives here. We're going on an investigation to find the clues, the key numbers and constants that biochemists use to figure out just what makes these tiny machines tick.
Okay, so our first clue comes from a pretty simple observation. If you give an enzyme more of its fuel, that is, the specific molecule it works on, called the substrate, the reaction it's driving gets faster. But, and this is a huge but, only up to a point. It doesn't just keep getting faster and faster forever. Eventually, the whole process just hits a ceiling. It levels off.
And this plateau, this absolute top speed that the reaction can hit under these conditions, well, it has a name. We call it Vmax, which stands for maximum velocity. It's literally the fastest this group of enzyme molecules can possibly work, no matter how much more fuel you try to jam into the system. So, what's actually going on here?
Well, Vmax happens when the enzyme is what we call saturated. Every single enzyme molecule has its active site occupied and is busy processing a substrate. Just imagine a factory assembly line. Once every single worker on that line is busy, the factory just can't produce things any faster, right? Even if you pile up more raw materials at the door. That's Vmax. It's the enzyme running in top gear.
All right, so Vmax tells us the what, the maximum possible speed. But that's only half the story. It doesn't tell us how easily the enzyme gets up to that speed. For that, we need our next big clue, a value called the Michaelis constant, or just Km. This constant is the real key to understanding how responsive an enzyme is.
In other words, how much fuel does an enzyme need before it really starts to hit its stride? Is it super sensitive, getting up to speed with just a tiny amount of substrate? Or does it need a whole lot of it to really get going? This is what Km helps us figure out. It's basically a measure of an enzyme's affinity for its molecular partner. And here's the really cool practical definition of Km. It's not some abstract concept, it's a specific, measurable concentration. So if you figure out the Vmax, you can then find the exact amount of substrate it takes to get the reaction to run at half of that top speed. That concentration value is the Km. Simple as that. Let's break this down, because this is really important. A low Km is like a super efficient engine that gets to half its top speed with just a little bit of gas. It means the enzyme has a high affinity for its substrate. It binds it really well and gets to work fast. A high Km, on the other hand, means the enzyme is a bit more picky. It needs a lot more substrate around to get to that same halfway point. It just has a lower affinity.
And get this, Km is not some universal number. It is all over the place. Just look at hexokinase. For glucose, it has a tiny Km, which means it has a super high affinity. But for fructose, its Km is 30 times higher. It shows you just how specific these enzymes can be. The Km is like a unique fingerprint for every single enzyme-substrate pair.
Okay, so Vmax is great, but there's a catch. Its value totally depends on how much enzyme you actually have in your test tube. If you double the amount of enzyme, guess what? You double the Vmax. So how can we compare the true individual speed of one enzyme to another? We need a number that's completely independent of concentration. So that leads us to the next big question in our investigation. We need a way to talk about how fast a single enzyme molecule can do its job, once it's actually grabbed a substrate. And this is where we get to some truly mind-boggling numbers. And the answer is a little something called kcat, also known as the turnover number. And this is the metric we've been looking for. It tells us per second how many times one single enzyme molecule can perform its chemical magic. It's the enzyme's personal best, its absolute maximum processing speed when it's going all out. And let me tell you, the range here is absolutely staggering. I mean, look at the slow end. Reca protein does less than one reaction every 2 seconds. But then, look at the other end of the spectrum. Carbonic anhydrase can churn through 400,000 reactions per second. And the champion, catalase, an unbelievable 40 million reactions every single second. That's not just a supercar, that's a spaceship. Okay, so we've got these two major clues, right? We have kcat, which is just raw speed, and we have Km, which is all about responsiveness. But to really solve this case and find the ultimate measure of an enzyme's performance, we've got to combine them. I mean, an enzyme isn't really that great if it's lightning fast but has a terrible affinity for its substrate, is it?
And that's where the big reveal comes in, the ratio of kcat over km. This is called the specificity constant, and it is hands down the single best number for judging an enzyme's total catalytic efficiency. It perfectly captures both how fast the enzyme is and how good it is at finding and binding its target in the first place.
So you might be thinking, is there even a limit to this? Can an enzyme just get infinitely efficient? And the answer is, yeah, there's a hard limit. It's a physical speed limit. At the end of the day, an enzyme can't act on a substrate until it literally bumps into it. So the ultimate speed limit is simply the rate of diffusion, how fast molecules randomly find each other in a solution.
That number, that absolute physical speed limit, is somewhere between 10 to the 8th and 10 to the 9th. And here's the crazy part. Some enzymes are actually at that limit. Enzymes like acetylcholinesterase and fumarase have achieved what scientists call catalytic perfection. They're so incredibly efficient that the only thing holding them back is the time it takes for the next substrate molecule to just float on over.
Okay, this is all fascinating theory, but how do scientists actually measure this stuff in the lab? I mean, you can't just look at a curve on a graph and perfectly guess where Vmax is. It's an asymptote. Well, they came up with a really clever tool to get around that. You see, the problem with that standard reaction curve is that, well, it's a curve. It kind of flattens out and just approaches Vmax, but it never really technically touches it. That makes it a real pain to measure precisely. So biochemists came up with this brilliant mathematical workaround called the Lineweaver-Burk plot. So what these brilliant biochemists figured out is that if you plot the reciprocal of the velocity against the reciprocal of the substrate concentration, that tricky curve magically transforms into a perfectly straight line. And from there, it's super easy. The y-intercept gives you a precise value for Vmax, and the x-intercept gives you Km. It's just an elegant solution that is also incredibly helpful for studying how drugs mess with enzymes. And this is where all of this gets really, really important. Understanding enzyme kinetics isn't just some academic exercise. The molecules that interfere with enzymes, inhibitors, are the foundation for so many of our most important drugs. Just think about aspirin. It works by inhibiting an enzyme that's involved in making pain signals.
A really common way this works is called competitive inhibition. Basically, a drug molecule is designed to look a whole lot like the enzyme's normal substrate. It's a look-alike. It then competes for the exact same parking spot, the enzyme's active site. And if the inhibitor gets there first, it blocks the real substrate from getting in, and the whole reaction slows down or just stops completely.
And this really is where it all comes together. By understanding an enzyme's Vmax, its Km, and how different inhibitors change those numbers, scientists get the clues they need to design better, more specific drugs. Which leaves us with a pretty powerful final thought. If we can perfectly map the speed, the efficiency, and the responsiveness of a critical enzyme, can we then design the perfect molecular key to control it? The answer to that question? Well, it's at the very heart of modern medicine.